It is integrating this thing over an odd curve. They gave this x plus y equals 1 in the complex plane. They didn't just write it as some segment, they actually extended an infinite line. Okay? The whole line. So, and with the orientation going from top to bottom, x coordinate increasing. So I summarize the problem in this way. But the way we're going to approach is that we look at actually finite line segment along that, and g1 is going to the left above, and g2 is going down to the right down there, right? So independently, it's not like perfect symmetry. There's independently approaching. Okay? Remember when you calculate indefinite integral, something like that, you have to let this one and that one as two separate infinite approach. Okay, not necessarily canceling or anything. All right, so here I'm looking at the antiderivative. You know this problem from the real calculus problem. It always enter arc 10, right? Because this guy didn't factor. Z squared plus 4 over there is showing, right? Z squared plus 4 doesn't factor. But if it factors, you enter partial fraction decomposition, right? If this were z squared minus 4, then you will enter partial fraction decomposition and enter log. But does it factor over complex? Yes, everything factor over complex. It's called fundamental theorem of algebra. Any polynomial I give you, that's going to completely factor over the linear integers, linear complex numbers. It's called fundamental theorem of algebra. So here we have this thing. I factored it. Z plus 2i and z minus 2i, right? And then you do the partial fraction decomposition. Whatever that is, and it looks like this. I over 4, some constant business, and z plus 2i minus z minus 2i. Then what is the antiderivative of this one? Log, principal log. What is the antiderivative of that one? Principal log. So in the book, it goes through arc10 and rewrite it as log. We're just directly going into log, right? And it actually, this thing explains a lot of phenomena in the real integration business that you might saw the similarity in the shape of the answer, but they're kind of coming from different world. All of them explain through what function? Exponential and logarithm, because it's the same function. In complex, there's only one elementary function. So we do that. So I wrote down this, what is it? Antiderivative of this integrand function, right? So I did that. I'm not doing this I over 4 right now. Okay. So I looked at it here, and first, this is the thing I'm going to do, and then I'm going to put in z1 and z2 in there, and that's it. It's a fundamental theorem of complex integration, right? And see how the z2 and z1 behaves as it goes to the infinity in that line. But I realize that these two guys has what? Branch cut, right? And this line happened to get in the way of that branch cut right there. So I had to separate it, W1 and W2. And calculate this one. W1 is going very close to that branch cut. W2 is also, and Z1 is going to that infinity direction, and Z2 is going down to that infinity direction. Right? Really gets ugly business, but you can compare it with the other version. Still, you have to go around it. So I'm not sure which one is the easier way. This one is easy to figure out. The branch cut's easy, right? It's right away once you get used to it. So I did that calculation and see if it's there. So you're not going to like this. It just looks complicated. But if you do it yourself, and hey, this is fun. Just seeing someone else doing is not fun. But if you yourself do it, it's not. So I separated here from Z1 to W1. That's the what am I doing? Let me understand this one. I understand now. This only singularity is going through is this 2i branch cut, right? The z plus 2i here, that branch cut is not touched. Correct? Yeah, only branch cut is touched, the 2i. So for that function, log z plus 2i, that integration part has no way, there's no branch cut for this line is not hitting the branch cut of that part. So I'm just applying fundamental theorem here. Just plugging in for a second because this curve is not in the way of a branch cut of this guy here. Does that make sense? only this one has a branch cut, so I'm separating it here. So from Z1 to W1, that's what that is, Z1 to W1. And W2 to Z2, the W to the Z2. Okay? Now this one is a simple calculation here. Then you have to look at, as Z1 approaches infinity, what is the argument? If the Z1 approaches infinity, what do you think that argument is? 2i is kind of irrelevant. The Z1 is going to the infinity, where the 2,1 is almost like origin to the magnitude of a Z1. Does that make sense? Z1 is all the way out there in some galaxy, and you're down there here, 2i, that's almost treated as a 0. So argument of Z plus 2i is the same as argument of Z, the limit behavior. Does that make sense? I mean, here's a 0 and here's a 2i, right? Z is over here. This is the argument of Z minus 2i or Z plus 2i, whatever. Or Z is over, 0 is over here if it's Z plus 2i. And this is the argument of Z. Do you agree that if Z is going to that direction, this argument is almost the same, right? Just like a sun ray from the sun is almost a parallel when you observe it on the earth, right? That's the same phenomenon. It's too far away. This angle is the argument, and that angle is the argument. If it's far away, that's almost the same. So what is the argument there? This is, from here is almost 45 degree on the axis, so it's like 175 degree, 135 degree something. So 3 pi over 4. So that's why it's picking up 3 pi over 4 there in that one direction. So you have to look at all individual part. It's all about modulus and the argument behavior. And if you look closely and if you all patch together, all the lengths cancel out. And the way the length of lnz2 plus 2i, lnz2 minus 2i, they cancel out. Not exactly. They're different, right? But as you go, 2i is negligent as it gets larger and larger. And arguments survives, and all put them together became negative 2 pi I. Okay? But there was this I over 4 out there. If you multiply it, this is pi over 4. I looked at the answer. It was pi over 2. So I got it right. Okay? All right. But our book actually, in other parts of the book, they should introduce this, antiderivative formula in a slightly different way. It's just like log put together. Log z plus 2i divided by log z minus 2i. Okay? So I looked at that one too. All right, here's an alternative one. We're looking at the same thing, but when you put the log together, maybe you can argue that, this can be an antiderivative. Don't think too much about when you put the log together and separate it. There's something you have to be careful about, right? Remember that part? The argument doesn't behave too much additively. If it is getting the different range of negative pi to pi, you have to add 2 pi I back and forth to make it an issue. But they all go into C here. Does that make sense? Whatever the 2 pi I pops out to make this one happen, to shove it into C. Is that okay? So that you can actually verify by differentiating here, and you recover this. A different argument to show this is correct on antiderivative. Any question? Now you have to look at what is the branch cut of this one. That's a harder calculation than the branch cut I had before. 2 slits, it was really easy to pull out, right? Because it's separated. Now you have to go carefully like this. Whenever this thing inside the log is a negative real integer, a real number, that's the branch cut, right? So I put the negative t and solve for z. So you started here. This is going to be negative t, where t is a positive real number, so negative t, negative real number, right? That's it. So I solved it, and then that was a parametric equation. It's a real number multiplied by I, so it's all in the vertical axis. And I plug in t equals 0 and 1 and 2 to figure out what those are. And it turns out is this little slit. When t equals 0, 0, 0, negative 2i, right? It's negative 2i. Realize that as you plug in more and larger value, it's not going up to infinity. If t approaches infinity, you see that t cancel as t approaches infinity? That becomes 2, so it picks up 2i. So the entire positive real number parameterization is only giving you a finite length. So that's the branch cut of this guy. Different from earlier version. That's a strange thing, but you have to be careful. You have to clearly calculate the branch cut in this way. Don't think that was the same function algebraically, isn't it? So it must be the same branch cut. This putting it into a quotient like that changed this idea of the branch cut. But all these things gives you the same answer in the end when you calculate antiderivative. So here's a line, right? Z1 through Z2. That still passes through that branch cut right there, right? So it causes a little bit of problem. This time you have to calculate this argument calculation. Branch cut is one branch cut. It's kind of clean calculation here, but I find this argument calculation gets even more complicated. And here is the picture. Let me just use this picture. So here, I wrote it down. So the Z1 to W1 and W to the Z2. That's the integration have to be separated. Does that make sense? Yeah. So I'm plugging in Z1 and Z2 and W1 and W2 all in this form. Already plugged in. One fundamental theorem here, another fundamental theorem there. Things like that. So when I plug in Z2 and W2, now Z2 is going to approach infinity, right? When Z2 is going to infinity, 2i doesn't matter. It's approaching 1 anyway, right? So what is log of 1? 0. It's approaching 0. The same thing for 0. So this picks up all the rest of the part. To me, this hardest part was the angle. So I looked at it carefully. W2 plus 2i. So W plus 2i is this one. 2i to the W2. That's that direction. You see that? W2 minus 2i is this vector W2 to negative 2i. So that's this W plus 2i. Okay? Vector, you have to subtract the 2 points. So the vector W plus 2i is this vector starting from negative 2i to the W2i. And the other one in the denominator, W2i minus I, is that W2 is here, 2i is there, right? So it's kind of in this direction. W2i minus down there. Okay, so yeah, let's keep it that way. So if you take the quotient, how is the argument behaves? Subtraction, right? The angle. So the angle between these ones, between this one. So that's almost getting pi because you can see that W2 approaches that point right there. Then this angle here is almost vertical, right? So that becomes almost vertical. What about W2 minus 2i? That's down there, this one. That one almost vertical too, right? So this angle approaches what angle? Pi, almost pi, the angle difference in there, right? But there's a little subscript there. What is that? It's not a typo. Negative. What does that mean? Approaching from pi a little bit low. Slightly smaller than pi, right? That's the behavior in here. The argument of this guy behaving. I looked at this one in a similar fashion. W1 plus 2i's. W1 is over there. Negative 2i is down there. So that's the vector right there. So I sketched it W1 plus 2i. So isn't that direction slightly to the left of the vertical line? That's the vector there. Correct? That's down there. This point is position is exactly negative 2i. Going from here to the W1. That's that vector. I'm transporting this vector W1, 2i to the W1. So that will be W1 minus 2i. So that's down there, W1 minus 2i, but it's transported. And it's going that direction. So this one, again, the difference of angle. So going from here to there, they're already also being almost vertical. But this time, it's slightly more than pi, right? It's always slightly more than pi and becoming almost a pi. But what does log pick up? An angle that is slightly bigger than pi. You're looking at a complex number whose argument is slightly bigger than pi. If you hit the principal log, what does that pick up? Though this is approaching pi from above, when you hit it log, this picks up almost a negative pi. So these two things will together will give you negative 2 pi I again. Everything else cancel. 0. So you get pi over 2 again. Alright, that's the business. Whenever your curve hits the branch cut, and this is the interpretation.